Good morning. Welcome to our makeup session for the October 15th class. So I'm actually at home. I'm recording this and I'm hoping all the technology will actually work out. So today what we're going to do is we're going to, first of all, review some of the basics that we learned about series and some of the tests that we learned. And then I'm going to actually introduce a new test to you called the ratio test. That will be very important in analyzing what are called power series. And power series we'll study in the next couple weeks. All right, so let me get started. So first of all, I have to share screen. There we go. All right, so the first thing I want to sort of review is the notion of sequences. Okay. So remember what a sequence was. A sequence was just a string of numbers, right, which is ordered. And we denote the sequence by AN, okay? And so let me give you some examples of sequences. So we can take the sequence 1 over n. And what does that look like? Well, it looks like 1, 1/2, 1/3, so forth and so on, right? You could also take, for example, the sequence 1 over n to the 4th. And what does that look like? Well, it's, let's say 1 over 2 to the 4th, 1 over 3 to the 4th, so forth and so on. Now, a lot of times these sequences actually look like functions. So for example, we could think of the function f of x equal to 1 over x in the first example. And we could think of the function like f of x being equal to 1 over x to the 4th in the second example. So when you actually can think of the sequence as a function, then we could talk about the limit of a sequence. So if f is a function on the real numbers, and f of n is equal to an for, let's say, n equals 1, 2, and so forth, then when I take the limit as n tends to infinity of the sequence, that's the same thing as the limit as x tends to infinity of the function itself. Okay, so for example, in the first case, if I take the limit of 1 over n, that's like the limit of 1 over x as x goes to infinity, and so that sequence will tend to 0. Okay, so the next thing we talked about was the notion of series. So remember what a series was, it's basically an infinite sum. So the way we write a series typically is the summation from n equals 1 to infinity of an. So an example of these are, let's say, the sum from n equals 1 to infinity of 1 over n, which we have seen diverges, and the sum from n equals 1 to infinity of 1 over like n squared, and that converges to a finite number. So when we talk about convergence of series, what we have to do is we have to look at the partial sums. So when we look at the partial sums, we have the partial sum S1, which is the first term, S2, which is the sum of the first two terms, and the nth partial sum is the sum of the nth terms, the first n terms. And we think of the partial sums as a sequence. So the partial sums, this forms a sequence. And so the series converges if and only if this sequence has a limit. So we have that if the limit as n tends to infinity of Sn, this limit is finite, then the series converges. And if it's not finite, then the series diverges. Okay. All right, so the name of the game in the last several lectures has been to actually figure out tests for convergence of series. And so we have various tests. So the easiest test to actually use is called the limit test. So the limit test just says the following. So if the limit of the entries in the sum is not equal to 0, then the series diverges. All right, so this is the easiest test to apply to conclude divergence. This test does not test convergence, it only tests divergence. So let me give you an example of this. So suppose I take the sum from n equals 1 to infinity of sine of n. Okay, so we know what the sine function looks like. It oscillates up and down between 0 and 2 pi. And so as you go out to infinity, well, this is the same as taking the limit as x goes to infinity of sine of x. And this limit does not exist. Okay. So because it's not finite, this series diverges. All right, so that's the limit test. And so we can use that in various examples, but usually doesn't cover, like all examples. All right, so the next thing we learned about was the geometric series. And the geometric series looks like the following. So it's a sum from n equals 0 to infinity, AR to the n, okay? And the absolute value of R is going to be positive. Okay? Now, what we did was we actually learned about the geometric series, and we learned about properties of the geometric series. So one thing we learned was when R is bigger than 1 in absolute value, this diverges by the limit test. So this diverges when the absolute value of R is strictly bigger than 1. And then we looked at the partial sums, and we actually saw that it actually converges when the absolute value is less than 1. So the divergence should actually be bigger than or equal to 1. And it converges in this range. Okay. And in this case, the sum here is equal to the following formula. It's A over 1 minus R. And what we did was we actually looked at, various examples of how to use the geometric series. For example, the superball problem, and also the problem involving applying it to repeated decimal expansions and converting those into fractions. All right. Now, the first sort of real test that we looked at was the integral test. Okay, so the integral test basically allows you to test convergence and divergence of series by using improper integrals. So let an be positive. Okay, so I want all the terms in the series to be positive. And let's say f of n, so f is a function, equals an, where f is also positive and integrable. So you can actually find out what the integral is. Okay, so then the integral test says that the sum, let's say from n equals 1 to infinity of an, is going to converge, let's say respectively diverge, if and only if the integral from 1 to infinity of f of x dx converges or diverges. All right, so you can actually test the convergence and divergence by just taking the improper integral. So we use this to figure out what convergence and divergence was for these harmonic series and other series like it. So here's an example where we use the integral test. So the summation of 1 over n to the p, this converges for p larger than 1 and diverges when p is between 0 and it's less than or equal to 1. And the way we actually showed that was we just evaluated the improper integral. And the improper integral, the corresponding improper integral, has the convergence and divergence property similar to what I just wrote down. All right, so that's the integral test. And so this past week, we learned about 2 tests. And so I'll go over those right now. So one is the comparison test, and one is the other one is the limit comparison test. All right, I guess we also call this the direct comparison test. 2. All right, so the direct comparison test just directly compares series, right? We just do it sort of term by term. So it says the following. So suppose we have 2 series, one involving ANs, the other involving BNs. Okay. So the first thing is, if the summation of the BNs converge, then the series involving the ANs also converge. Okay, so just from common sense, the series for the BNs is bigger than the series for the ANs, and the series for the BNs is a finite number, so the series for the ANs has to also be a finite number too. Okay. And similarly, if the summation of the ANs diverge, then the series for the BNs diverge too. Okay. So let me again give you an example of how one can use this. So suppose you take the sum, let's say n equals 1 to infinity natural log of n over n. Okay, so, we just have to make, an observation about the natural log function. Okay, so what does the natural log function look like? Well, it kind of looks like this. So this is y equals natural log of x. Okay. Now, the point is that for n large, then the natural log function is bigger than 1. So here's 1 out here, and this is e over here. And so if you look at it, the natural log will be bigger than 1 for values bigger than e. So basically, the natural log of n is going to be sort of bigger than 1 for n large. Okay. So really, if we want to look at the convergence or divergence of the series, we could just make n to be past e. So we can actually consider the series, I don't know, n equals, let's say 4 to infinity natural log n over n, because we know 4 is bigger than e. Okay. So when n is at least 4, we know that the natural log is bigger than 1. All right. So that means that when I take 1 over n, the natural log of n over n is going to be dominate 1 over n. Okay, it's going to be larger, bigger than or equal to 1 over n. And now what we can do is we can use the direct comparison test. So by the direct comparison test, the sum from, let's say, n equals 4 to infinity 1 over n will diverge. Well, we know this diverges. Let me say it this way. Sorry. The nice thing is I have a good eraser with this. Okay, so I should clean up my argument a little bit. So by the p-test, this thing diverges. Okay, actually, let's clean that up a little bit more too. It erases much better on the iPad than on a whiteboard. Okay, that looks much better. Okay, so by the p-test, we know that thing diverges. And now by the direct comparison test, the series converges. So by the direct comparison test, the summation n equals 4 to infinity of ln n over n diverges. So, it doesn't matter if I just add a few more terms like n equals 1, n equals 2, and n equals 3. So the sum from n equals 1 to infinity ln n over n also diverges. Okay, so that's a application of the direct comparison test. All right, so now let's talk about the limit comparison test. Okay, so that's next. All right, so the limit comparison test, what it's good for is that sometimes we just can't compare the values of the entire series with one another. I mean, what we want to do is we actually want to sort of compare the ratios. And that turns out to be an easier test to actually try to apply. So suppose that AN and BN are positive, and we have series AN and a series BN. Okay, so these are both series. So if the limit as n tends to infinity of AN over BN is equal to a finite number, then the series converge. So this series converges if and only if this series converges. So what this means is that one series will converge, then the other series converges. If one series diverges, then the other series will also diverge too. So these series are somewhat comparable in terms of convergence and divergence. That's what this test says. Okay, so one very nice application of this is with quotients of polynomials. So we've done several examples of this. So let me kind of run through this fairly quickly. So let's say I take n cubed plus 10n all over n to the 5th plus 2n cubed plus 5. All right, so we sort of examine this series, and we have a cubic on top, and we have a 5th degree polynomial on the bottom. So when you kind of think about this, the terms in the series are going to sort of grow in terms of 1 over n squared. Okay, so we should actually compare this to the series n equals 1 to infinity 1 over n squared. Okay, so these should be fairly close in some sense in terms of convergence and divergence. Now, we know that the series 1 over n squared actually converges by the integral test or the p-test. So converges by the p-test. So if the limit comparison test works here, then we can conclude that the top series, the one that I presented first, will also converge. All right, so let's try to apply the limit comparison test. So I want to take the limit as n tends to infinity of the top series, n cubed plus 10n, all over n to the 5th plus 2n cubed plus 5, and then all over 1 over n squared. All right, so the 1 over n squared gets moved to the top. So this limit is equal to, remember, use equal signs. Limit as n tends to infinity, n cubed plus 10n all over n to the 5th plus 2n cubed plus 5 times n squared. This is the limit as n tends to infinity. Okay, so I'm just going to multiply in the n squared. All right, so this is going to be n to the 5th plus 10n cubed all over n to the 5th plus 2n cubed plus 5. Okay, so now at this stage, we sort of see that we have a 5th degree polynomial on top, we have a 5th degree polynomial on the bottom. We want to take the limit. This is an indeterminate form. We can use L'Hopital's rule 5 times, but there's a quicker trick, is to multiply top and bottom by 1 over n to the 5th. So let's do that. Okay, so I'm multiplying top and bottom by 1 over n to the 5th. It doesn't change anything. So this is the limit as n tends to infinity. So I get 1 plus 10 over n squared. I get 1 plus 2 over n squared plus 5 over n to the 5th. Okay, so notice that 10n squared, 2n squared, 5n to the 5th, as n goes to infinity, they all go to 0. And so, as you would expect, the limit is 1, which of course is a finite number. So by now, the limit comparison test, this series that we had before, n equals 1 to infinity, n cubed plus 10n over n to the 5th plus 2n cubed plus 5, this will also converge. Okay, we'll take a slight pause. At this point, if I was actually live online, I would actually ask if there are any questions. But let me just pause just for a second. All right, so the next thing we're going to talk about is the ratio test. So this is new material. So let me kind of draw a line here. I can sort of draw a line. So the previous stuff was just review. Maybe I'll draw 2 lines. Looks a little bit better. All right. Okay, so now I'm going to talk about what's called the ratio test. All right. Now, let me give you the philosophy between the ratio test. The ratio test tends to be the easiest test to apply in some ways, because you're just looking at ratios of terms. You're looking at limits of ratios of terms. You're just sort of determining whether they're less than or 1 or bigger than 1. But at the same time, the ratio test can be inconclusive. So if the limit of the terms, the ratio of the terms goes to 1, then we cannot say anything. So either the series could converge, it could diverge, we just don't know. Okay. All right, so let me state the ratio test. So let the summation of an be a series with, let's say the terms are non-zero. So just remove all the 0 terms. Okay. So first thing, so if the limit as n tends to infinity of the terms an plus 1 over an, if they're strictly less than 1, so you take the absolute value of the ratios of the terms, the next term over the previous term. Okay, so you take that limit as n goes to infinity. If it's less than 1, then the series converges. Okay, So 2. So if it's the limit is bigger than 1, the series diverges. And actually, the convergence is absolute. Okay, so we can say a little bit more than just converge. So this series will actually converge in absolute value. And as we've seen before, if it converges in absolute value, it converges also. So if the limit as n tends to infinity of an plus 1 over an is bigger than 1, then this series diverges. Okay. And 3, if, well, there's only one other case, right? It has to be equal to 1. So if the limit as n tends to infinity of an plus 1 over an, this is actually equal to 1, then we can't say anything. I mean, it could converge, it could diverge. It's inconclusive. You know, as I've mentioned before, these tests are like medical tests. You know, sometimes you can say something, so one way or the other, but they can be inconclusive. So then this test is inconclusive. All right. So what I'd like to do is just give you an idea why this works. And it's kind of a cool idea because the ratio test sort of depends on the geometric series. So let me give you a little bit of a justification. All right. So let's look at case 1. So look at the first part here. So suppose the limit is less than 1. So let the limit as n tends to infinity of an plus 1 over an. Suppose this is actually equal to some number r, which is less than 1. Okay, so because the limit is small r, that means that for large enough values, we know that this limit is going to be bigger than a number between r and 1. So I can choose a number, capital R, which is just maybe above little r, so that for n larger than capital N, we have that the absolute value of an plus 1 over an is less than r. Okay. All right, so this is sort of just using the definition of the limit that eventually we have to approach little r. So that means that we have to sort of be in between r and minus r in order to make this work. Okay. All right. Actually, r plus epsilon and r minus epsilon. All right, so what does this say? Well, the first thing it says is that if I take the term an plus 1, this is going to be less than r times a capital N. Okay, so that says the first thing. And then if I take the second one, that's an plus 2, we know that this is less than r of an plus 1. And then I use the first one, and so this is less than or equal to r squared of an. Okay, and then you could sort of go on and on. So notice that we're sort of bounding the series in absolute value by these terms. Okay, so if I take, so consider the series where I start from let's say n equals n plus 1 of an in absolute value to infinity. And this is going to be less than or equal to the sum from n equals 1 to infinity of the absolute value of an r to the n. Okay, so I've just sort of rewritten one series in terms of the other. Okay, so this is the left-hand side over here, and this is the right-hand side. So now we know that r is less than 1, and this is a geometric series. And so this series converges. And then by direct comparison tests, the series on the left has to converge. So by the direct comparison test, this series converges. So this series that we started off with, well, it converges in absolute value, right? So now we can just say it absolutely converges. All right, so that gives you kind of a flavor for how you can use the geometric series convergence to actually show the ratio test. And you can do it for part 2 also. You can actually make certain bounds, and then you can show that because r is strictly bigger than 1, then you can actually show the divergence also using the geometric series. All right, so let me give you an example, a couple of examples of how we use the ratio test. So I actually write examples out. I won't use the abbreviation. All right, so here's the first example. So you have this kind of weird series. So that it's n to the n over n factorial. Oops. Okay. Sorry about that. Just tapped on the wrong thing. All right. So this looks like a kind of strange series, and you kind of throw up your hands and say, oh, yeah, I really don't. I mean, what am I going to do with this? Well, this shows you where the ratio test is actually useful. So first of all, let's recall what n factorial is. So that's the numbers n minus 1. So it's the product of the numbers from 1 to n. Okay. And so we're going to apply the ratio test. So apply ratio test. All right. So let's just write out what an plus 1 is. So that's n plus 1 all over n plus 1 factorial. And an is just going to be equal to, sorry about that. Let me just clean it up. Okay, so it's n to the n over n factorial. Okay, so let's write out the limit as n tends to infinity. So what I find useful is if I have a quotient, then I sort of write a slash notation up on top so that I can see which terms will cancel out. Okay, slash n plus 1 factorial. Okay, so that's the numerator. And then the denominator term is this over n factorial. So the n factorial will go up to the top. The n plus 1 factorial will go down to the bottom. So of course, this is an absolute value. So this is the limit as n tends to infinity of, now I could write it out as two terms. Here I got n plus 1 over n plus 1 over n to the n. And then I have, on top, I have n factorial. On the bottom, I have n plus 1 factorial. Okay. Now, if you look at the definition of factorial up here, if I take n plus 1 factorial, that's the same as n plus 1 times n factorial. So you can actually get n plus 1 factorial by just multiplying n factorial times n plus 1. All right? Okay, so this is the limit as n tends to infinity. Let's keep this the same. And this is 1 over n. All right? And now what I can do is I could sort of, oops, I'm missing an absolute value. I can put the n in with the n to the n. Okay, so this is like the first power here. So I'm just going to add exponents together. Okay, so this is going to be the limit as n tends to infinity of n plus 1 to the n plus 1 all over n to the n plus 1. Okay. And now I could just use my sort of law of exponents, since n plus 1 is the exponent both on the top and on the bottom. And this is going to be the limit as n tends to infinity of n plus 1 over n plus 1. Okay. So this is the limit as n tends to infinity of 1 plus 1 over n. And then I'll use one of the n's over here and 1 plus 1 over n like that. Okay. Now, if I take n to go to infinity, the second term is going to go to 1. Okay. And then the first term is just the definition of the number e. So e times 1 is e. So the limit is e. And we know that e is like 2.718. That's clearly bigger than 1. So by the ratio test, part B, or part 2 over here, this series has to diverge. So therefore, this series diverges. Okay. Now, let me show you another situation that you can actually do or use the ratio test on. So as you can see, the nice thing about the ratio test is you can apply it to very, very complicated series. A series that you would not be able to do the integral test, or a series that you would not be able to use like even limit comparison because you don't have another series around. You could just take that series and sort of analyze it in some ways using quotients of terms. All right, so let me give you another example. So the sum, n equals 1 to infinity, n to the fourth, all over minus 4 to the n. Okay, so now we can just apply the ratio test. So the limit as n tends to infinity of an plus 1 over an. So we just have to make sure that we write out the terms carefully. So an plus 1, we replace n by n plus 1. So that's going to be n plus 1 to the fourth. Again, I'll use this kind of notation so that I can kind of keep everything straight. So minus 4 to the n plus 1. Okay, and then I'll make a bigger fractional thing. Okay, so what is, when I put in n, I get n to the fourth over minus 4 to the n. Okay, so now I get the limit as n tends to infinity. Now let's separate things out. So I got n plus 1 to the fourth all over n to the fourth times, well, what do we get? We get this one up on top. So minus 4 to the n all over minus 4 to the n plus 1. Okay, so let me do a few more steps. So this is n plus 1 to the fourth over n to the fourth. This is minus, well, it sort of depends, but basically it's just minus 1 over 4. That's basically what it is. Okay, so that's 1/4. So the limit as n tends to infinity of n plus 1 over 4, n to the fourth, times 1/4. Okay. Now, we've evaluated, I mean, the first part is just polynomial of degree 4. So you get in the top and on the bottom too. So, you know, you could use L'Hopital's rule or use the same trick that I've had before. So the limit here goes to 1, right? So the total limit is going to be 1/4. And this is going to be, of course, strictly less than 1. And so this series converges. All right. So at this point, I would actually also ask if there are any questions. And so I'll just pause just for a second. All right, so I've actually given you a new test, the ratio test. We'll actually do more examples of the ratio test on Monday. And then on Monday, I'll also introduce what's called the root test. And then on Wednesday, we'll look at things like the alternating series test. That will actually conclude the tests that we go over, the convergence tests that we go over. And then we'll sort of move more in the power series the following week. And maybe we'll do some on Friday. So I wish everybody a happy and safe weekend, and go Dogs.